Make sure it's buffering there. Okay, so these lectures are going to be recorded on YouTube for later if you need them. And I have to hit this button right here. Okay, so you can look at all the information about this class if you go to robjorstad.com. You could go to Canvas. There's lots of different ways to see all the different handouts and things. Included somewhere in there is the syllabus. You can go and read that at your leisure. I encourage you to skim through it at least and maybe read all the technical details about grading and stuff. In general, the first week of this course is very different than all the other weeks. It's a little bit weird. We're covering things that in theory you're supposed to already know at least a little bit. Some of you may not know them, and that's fine too. But so we're going to be talking about sig figs, units, and vectors, stuff that was the subject of Physics 110. My goal is to finish chapter 1 today and then finish chapter 3 on Wednesday. Seems like a lot. Then after that, we'll kind of slow down. All right. So just be aware. And if some of this is too boring for you, at any time, if you want, on Canvas, I've already given you a list of all the homework for the whole semester. And whoops, I've got to get mine here. And especially those of you on Zoom today, I'm worried that you're going to get bored because at some point, I'm going to be walking around the class talking to the people in here. Alan, you could maybe say something in the chat there, and whatever. You could see that Alan Rubalcava is in the Zoom room with you. He's a learning assistant. He's had me for 110, 161, and 163. So if you have a question about like how to deal with me as an instructor or whatever, you can ask him. If you here in the class want to talk to him, you can join Zoom as well. And then you can talk to him directly. And I don't need to know about it if you don't want. His email is going to be on the Canvas website a little bit later tonight. I'm getting it up there. So Alan is a great resource that we have for this course. He's our learning assistant, and he'll be in class a lot of the time too, but he's just out sick today, so he's on Zoom. But those of you on Zoom, Alan, maybe you could send them the Physics 110 test 1, and they could, if this class is not working for you on Zoom, you could just take that old 110 test, look at the solutions, or you could work on the problems out of the homework. And that's where I was going next. So I know you've probably heard all kinds of stories about me as an instructor. One thing is I want you to succeed. So I try to make everything as easy as possible to get. So like all your academic resources for this class, so you know what's expected of you, and then it's just on you to do the work. You probably had tons of teachers say, oh, you got to work 2 hours outside of class for every hour in. And I bet to a number, it's never been true. In this class, the opposite is true. You probably should do more than 2 hours per week. Now, if you don't believe me, try me on test 1. And it always happens. Yeah, but I want you to succeed. I know you guys are pretty smart. You've never had to work that hard before. This is the class where it kind of changes and you actually have to start working hard, right? Life's probably been pretty easy for you academically until now. And this first week is going to seem too easy. And then what happens is maybe you don't quite practice enough. And then you maybe forget it. And then you miss the easy points in the class. And then the class gets really hard and you're toast. So do whatever you got to do to try and stay motivated. And to that end, I just printed out the homework for the semester right here. I stuck it in my book. You can do this when you get home. And then anytime you're bored in class, just pick a problem and work. And just keep working and always be working. The more you get done in class, the less you do outside. You know what I'm saying?
Are the problems that are recommended also, do they help you get prepared for the test?
Yeah. Here's the deal. We're all different, right? Everybody has a different level of preparation coming into this class, different life experience coming into here, right? So for you, the recommended, maybe you need to do half of them. Maybe somebody else needs to do 75% of them. Somebody might need to do none of them. Now, there's also a bunch of practice tests that you're going to want to take too. I've got 4 old practice tests for each test.
Awesome.
So what you want to do is if you do all of these and then take the practice tests, you're probably going to get an A, right? You know what I'm saying? Or at least a B, right? But getting an A in this class is not like trivial. Okay, getting a C in this class is not trivial. You got to work for it. But if you work, you're going to do it, right? The only thing that's going to get you is not doing the work. And this is the other thing. If you don't start early, like you'd be like, I'll just catch up. I had one student, they would just wait till the test. They would work 40 hours straight on my class and they got C's. So that's the way you want to do it, you could do that too. But if you do 10 hours a week, then do 10 extra hours the week of the test, study a couple, you'd probably get an A or B. Okay? Yeah. All right. So I'm not going to grade any homework though, right? So we'll just be doing labs and stuff. And other questions? Or from Zoom. On Zoom, if you guys ever have questions, I see a chat there. Okay. Oh, that was just Alan, my bad. Yeah. So Zoom, this will tell you something. If you mention something, Alan's there to kind of say, Alan can speak up and say, dude, you forgot to read the chat, something like that. So he's going to be helping me monitor that as well. But you can also, at any time, if you're on Zoom, all you got to do is just unmute and say, wait. And then we should be able to hear it in the class and it shouldn't feedback. So I respond pretty well if you ask them. So don't ever feel shy about interrupting me. And that goes for you all here in class too. Just if you're not sure, just say, hey, what does that to mean? Or wait, could you say that again? Just interrupt me whenever. Slow me down. All right. Okay. I want to get into it. I don't really want to spend any more time talking about this stuff. Well, I'm hoping that maybe next week after things get rolling, we'll know a little bit more about COVID and how that's going. And hopefully things are going to calm down and maybe it'll almost be a normal semester after this messy start that we're having. And I feel optimistic. It's kind of nice to have the bad crap happen right now. I think it'll be easier to recover now from all this weird stuff. So, okay. Let's go to page 1. Actually, I'm going to show you a couple of things really quick on the big screen. And again, if you already know all this, you can just start working on problems. Just so we're all on the same page. Let's see here. Let me do this. And I'm not offended if you grab a laptop or be looking around on your phone. That doesn't bother me at all. As long as you're working on physics, let's just rock, do it. Let me just a second here. So then I have to think. So for you on Zoom, I'm just trying to get something ready on a monitor here. Let me see if I could. Okay, so hopefully you on Zoom are seeing this, and then wait, which one do I need to do? This one? Oops. Give me just a second. Oops, wrong button right there. Okay. My website is crappy. It's designed by me, but it's got the links. All I care about is the content. So you can hopefully see this up here. I guess I could bring up the other screen too. I apologize for that. Just making sure you can navigate this. And once I show you a few things, I think you could be off to the races on your own here if you want. I need to update this. I just noticed it's still fall. I forgot I updated this on my Excel file and then I forgot to paste it. So I'll fix that tonight. Obviously, we are not physics 163. All right, and the times aren't quite right and the room's obviously not right either. So I'll fix that all tonight. So here's the deal. In class, basically bring this every time. And then on the laptops, so this is robjorstad.com, boring. But if you click the workbook, if you don't have the hard copy already, right here, this link, that's chapter 1. So you could use that today if you don't have it. Okay, and then the solutions to chapter 1 are right down here. Get a different color here. All right, so there's the solutions. And if we click on that, there you go. Now, some of you may have an older version of these. And so maybe I'll do this really quick. If you have an older version of the workbook, sometimes I do these weird problems that have fractions in them. And you may be saying, why does he have fractions in them? It's because some people still have the old book. Anytime they see a problem with a fraction in it, they'll be like, oh, I could just go to the website and get it right here if I don't have the fraction problems. So whatever. Most of you probably don't need to worry about that. So here's the deal. Maybe you know what you're doing. You're like, you know what? I'm going to do problem 26. If you hit Control F and type in 1.26, you're right there at the solution. And you can follow along so you don't have to listen to me if I'm too slow. And then every once in a while, if there's something we notice in class that's important, I'll be like, hey, everybody, oh, give me your attention just in case you don't know this. I want to make sure you understand this is important for my test. And I'll say something. I'll say, okay, back to work. All right. So that's kind of how I like to roll. And at the beginning of the semester, it's going to be all over the place because some people know this stuff already. Some people don't. It's going to be crazy. All right. So, but after 2 or 3 weeks, we'll start to come together and then we'll be working more together as a group. So I apologize if it's a little strange at the beginning. Any questions about where to find the solutions? Got that? So if you want, you can have that open and use them. My God, use these dang things. I spent forever. I've given up most of my life on these damn things. So if you're trying to learn and you're slow, read the solution and then learn from it. And then the next problem, try another one. And that's when you might go to the recommended list. If you find like, man, I still haven't been able to do any of the problems without the solutions, then you go to the recommended. Got it? And hopefully eventually you get to that where you could take these practice tests. Let's go to 161. You can see the old exams here. Look, there's just old tests and exams till you want to puke. Study guides everywhere, right? It's on you to do this. What's that? Oh, just robjorstead.com. So robjorstead.com, 161, or all these links are in Canvas as well. If you forget, just check Canvas. 161, there's the exams. So you can go nuts on there. And I write these solutions for you. There's a study guide right there. It tells you how I like to grade. So yeah, it's like, you can just start working. So a lot of you have had physics already. Maybe you're like, what does this person want? What does Jorstead want for the test? Well, there you go. Now you know what I expect. This shows you that. All right. Any questions about that? All right. So let's do that. Get out of there. Shrink this down. And now maybe let's talk a little bit about Sig Figs and let me. There's so many buttons these days doing the Zoom in room. I feel like a strange robot. All right. So Alan, can you hear me out there?
Yeah, I could hear you just fine.
All right. And then class in here, can you hear Alan all right? Okay, so Alan, I'm just going to be turning some lights on. Is there maybe 1 or 2 things you might suggest to these students? Because Alan knows what it's like to deal with me. And dude, you're not going to offend me. Just speak straight to him. What would you recommend to these students if you wanted them to pass my class? What could you tell them, Alan?
I'd say definitely take advantage of the practice exams he puts up in the website. I think they're a huge help. Yeah, they're really good study guides for you.
Got it. So practice today really helped, right? It's like gold, right?
Yes, sir.
How much homework did you do, Alan? Did you do any of it? Some of it, like?
I did all of it, all the recommended, all of the required. I even reviewed them at the end of or nearing the exams. So I did just about everything. And if I didn't have time, I would at least read the question, right? And then I would just look it up or look up the solutions really.
So like kind of read through it and think, oh, I bet you do this, this, and this, and then see if that was what happened in the solution.
Yeah, exactly.
Yeah, once you do enough of these, right, you don't want to write out every single freaking problem in this book. That's going to take you 10 years. That's what it took me. So, right, you might want to just look at it and say, huh, how would I do that? And then read the solution and see if I did what you thought. That's a way you can kind of speed up some of them. I agree. How many hours a week did you spend on 161, Alan? You had COVID 161 with me, didn't you?
Yeah,
That was
yeah,
hell.
yeah, it really was.
Yeah, that was brutal. But how much time were you spending?
On 161, I really don't remember. Probably roughly 10 hours a week, maybe.
Yeah,
So
yeah, it's pretty tough. So yeah, okay, but anyways, all right. Do any of you guys have any questions for Alan or anything you want to ask him? Or you could also send him an email once I get his thing up. Or is it all right? Let's do some problems, right? Thanks, Alan. You're the man. Okay, so let's look at page 1. All right. So and page 1 and page 6 kind of go together. I don't want to spend all day on this because in theory, this is supposed to be a review. How many sig figs does this number have? 4. So here's the thing. How many sig figs does this number have? 1. It's annoying, right? So this number here has 4 sig figs. And this number here has 1 sig fig. The rule that's involved here is the only one that's tricky. These are called trailing zeros because they're to the right of all other numbers. So these are trailing zeros. And so are these. Am I on the right monitor? I am. Okay. So in this case, if one of the trailing zeros is to the right of the decimal, it becomes significant, and then they're all significant. If none of them are to the right of the decimal, then none of them are considered significant. Now this is a problem because it's very difficult. What if I wanted to specify 100, but indicate it was sensitive in the ones column? There's a way we can do this. And so this is how I'm going to handle this in class. I would write a little line under here. If you ever see this in my work, which you'll see it all the time in the solutions, we'll talk about this in lab as well. So this is my way of indicating that a 0 is a significant digit, or it's the rounding digit. So this particular one would have 3 sig figs. All right. So if I got this trick from a chemistry teacher when I was an undergrad, so yes, even chemistry can be useful at times. There it is. Still use it to this day. That's supposed to be a joke, but I know you can't read it with my face, so whatever. I like to tease chemistry, but I actually like chemistry. All right, so we've got different ways to specify. If you don't underline anything, we go by the strict rules that you see on page 1. However, if you see this underline in my work, that's my way of telling you that one's significant. Is everybody okay with that? All right. Now, there's some rules there. I'm assuming you got, how many of you are familiar with sig figs a little bit? Just give me a thumbs up, thumbs down here. Okay, good. So let's go to page 6 really quick. Page 6. Here's where the stuff gets interesting. All right. I'm just going to put these rules up here real quick. Okay. Now, I'm not going to lie to you. On test one, I'm going to ask you a question and try to trip you up with Sig Figs. And I'm going to see if you remember to practice this, right? I'm going to show you how to do it right now, and you're going to know how to do it right now. And then you might forget to practice it again before the test. But if you practice it now, then review it before the test, this should be easy points. If not, it's going to be tricky. Okay, so let's give an example. Let's try 1.8D on page 7. And I want you to keep in mind the rules are on page 6 of the workbook. You can hopefully see how important it is to have the workbook here, okay? What did I say? 1.8D. I'm going to work out an example with you, all right? 1.8D, and it says, hopefully you remember scientific notation a little bit, but if not, we'll review that. So the idea here, we're trying to do this math, right? So before we get ahead of ourselves, how many sig figs does this number have? 3 sig fig. How about this one?
3.
This one?
3.
3. These are trailing zeros, but they're all to the right of the, or at least one is to the right of the decimal. So this also has 3 sig figs. All right. So if you had to guess, when we do this math, how many sig figs would you expect in the end?
3.
Okay, so my short answer is, if there's a subtraction, I don't know. It might be only 2, it might be only 1. Okay, and let's see how you could actually get, this is crazy, right? With 3 sig figs, I'm pretty sure we're going to end up with something other than 3 sig figs in our final answer. Let's follow it through. It's this one that messes with people, okay? This is the sig fig rule that people forget. They want to just say, oh, always keep the number. And they'd say 3, 3, 3. The final answer should have 3. Wrong. Let's do this subtraction right here. When we subtract this, what do you get? Oh, whoops, 2.01. Thank you. Right? Now, let's look at the column. This one is off in the tenths column. This one is off in the hundredths column. Which one should I keep according to this rule? The tenths or the hundredths? The tenths. So notice when we do this subtraction, we end up with fewer sig figs. Oh, so gee, I wonder what I might try to do to you on test day. I'll have an addition or subtraction where the number of sig figs is not what you expect, and if you forget the rule, you'll screw it up. All right, I'm not trying to lie to you. I'm just trying to keep you honest. All right. Why do we care about this at all? This is useful for estimating the uncertainty in a number. You don't see it right now. It just feels like boring rules. But if we don't do this, you're going to be wasting time on this later in lab. All right, let's keep going here. So what do we get? I'm going to say this is 2.01 times 8.00 times 10 to the 6th. Well, isn't it? I guess that's just going to be what? I'll get a, what, 2.16, wait, 16.08 times 10 to the 6th. Is that right? Hope I didn't screw that up. This one has 2 sig figs. This one has 3. How many sig figs should I have in the final output? We keep the number. And by this, I mean the smaller number of sig figs. So you're kind of, when we're doing sig figs, we're trying to keep track of errors without having to do real propagation of error. This is a trick that can save you lots of time in lab. So in this case, I want you to think about it as always trying to be the most conservative you can in these. You're always picking the crappier column, the furthest column that direction, or the smaller number of sig figs. So for this one, we choose just 2, right? So then the final answer for this would be 16 times 10 to the 6th, which is 1.6 times 10 to the 7th, all right? I hope I wrote down those numbers correctly. All right, so far so good with that? And so, all right, this is what you got to watch out for with sig figs. Tell me right now how you're feeling. Thumbs up, thumbs down on this. Okay, and thumb sideways is also legit answer. All right, do me a favor and kind of look at, if you're curious about rounding, I want to notice, I want you to point out, I want to point out something. Look at this number right here. Why didn't I just round it right here? I would have got the same answer in this case if I had just rounded it here. Bad form. You don't want to round till the very end. Look at page 6 at the bottom. There's a problem done correctly and a problem done incorrectly. Okay, when you look at that one, maybe I'll even write that up on the board here. I'm gonna run out of room, but just a sec here. Wrong way. Okay. So on page 6, that example, I'm going to walk you through this, even though it's there, just to make sure we understand why each step was done the way it was done. So I apologize, I have to write this up. All right. So in the first case, when you do this division, you get 1.58. How many sig figs should it have? If you're doing a division, what do? Do we keep the number of sig figs or the column of sig figs? The number. So that's 2. So that's right there. Alan, can you add them for me?
Yep.
Right on. The next number. 2 sig figs, 2 sig figs, multiplication division, keep 2 sig figs. So this is how that underline is kind of useful, even if it's not zeros. And then what do I get when I do this one? 0.729. Now notice this. I know this is boring, but I only want to have to say this once, because when I start taking out points on the test, you'll know why. Okay. In this case, you keep extra digits till the end of the problem. Now, this is no problem for you when you're working on your calculator or in Excel or in a computer on lab. So, right, if you're always using the answer button on your calculator, you're not rounding, and so this shouldn't be trouble for you. But where people run into trouble is they'll write down an answer on paper and round it, and then use that rounded answer. And if we have 5, 6, 7, 8 steps, man, by the time you get to the end, you've made so many rounding errors, your number is off, and I take off points. Okay, let's keep going. The next line, what did this turn out to be? 0.45. How many sig figs? Let's get that pink so it stands out. How many sig figs does this number have here if we use the correct rounding digit? 2, right? Because I've written 3, but it's represented as a 2 sig fig number. That's what that's supposed to mean there. That underline shows that only 2 of the digits are significant. Does that make sense? This one, 2. So how many should this one have?
Should be in the 10th place because we're supposed to keep the column.
Good. I was trying to mess with you. Good. Nice. So again, we'd have to use the addition subtraction rule. So it's in the 10th column, which matches both of these. All right. Is everybody kind of getting the hang of this? All right. And I think I dropped a square, didn't I?
Yeah, I was just about to say that.
Thanks. And when we do this one, you can follow the rest of the work and see that through. Well, we're so close. Let's just do it. All right. Now this has one sig fig. When you square it, that's basically multiplication. So I still end up with one sig fig. One sig fig. You do that subtraction in your calculator. What do I get? Whoops, 526, I think. And so here, this one's off in the tenths, this one's off in the hundredths. I keep the crappier of the two, the less precise of the two, the tenths column. Right? And so then if you wanted to write your final answer on my test, I'd probably be okay with that. But on an engineering class, we probably want to actually round it. And you could see, the whole point of this was to show you, if you don't round, you get one answer, and then look what happens to in the table right next to it. If you round it at each step, you're off by 20%. Now keep in mind, this only was 1, 2, 3, 4, 5 lines of work. So in 5 lines of work, these little errors from rounding could, in theory, add up to 20%. Obviously, I handpicked this example to be super dramatic. Usually it's not this dramatic. But this will always happen to you if you round too early. I think that's enough said on that. Agreed? So don't round too early. All right. It can sometimes screw you up. Pretty rare, but it does happen. All right. What do you think? You guys want to try a problem and see how we do here? All right. On page 7, any of those problems are kind of looking like a test level problem. Why don't you try, let's try 1.14. Try that. And in particular, I want to emphasize the 1/2 in question 1.14. So let me get back on the right whiteboard. Sorry, Zoomers. Let's go. Whoops, wrong one. There we go. So we're looking at 1.14. And you can race ahead if you want. I think this is one of your homework problems. I'll try to do as much of the homework in class as I can. What's that? It is?
Yeah.
Yeah, so you can see that I'm going to try to hook you up by doing some of this in class. So, right, if we can get 1/3 of your homework done in class, I feel that's great, right? That's my goal, but sometimes I fall short of that. I want to bring up one thing here before we get into this. Over here in the problem, I tell you what a sub x is equal to. I tell you what v0x is equal to, and t. I give you all those numbers, and I'll write them up here in just a minute, I swear. But I want to talk about this number right here. How many sig figs does that have in your mind? Oh, no. Power sig mode. Oh, there we go. Okay. Sorry about that. How many sig figs does this 1/2 have? What's your gut tell you? Or you could just read. Infinite. Basically, that 1/2 will have no effect on your sig figs. That's what I mean when I say it has infinite, right? Because aren't we usually going by the crappier column or the smaller number, right? If you have an infinite number of sig figs, this is never the limiting reagent, so to speak, for your sig figs. Like pi is another one of those numbers, right? Pi is an exact formula. It's the ratio of a circumference to a diameter. So it's exact. It has infinite sig figs. So where's this 1/2 come from? Does anybody know? Oh. This is just a look forwards. A is dv dt, right? So is it dv equal to a dt? And then when you integrate that, this is chapter 2 stuff, by the way. When you integrate that, this gives me v minus v initial or delta V. And over here, I get A times T minus T0, which I could set to 0. Well, I can rearrange this and say V equals V naught plus AT, right? Well, wait, isn't that dx dt? Oh, wait. Can I just cross multiply again? When you integrate this line, what are you going to get on that t? 1/2 AT squared, right? You see that when you integrate both sides of this, you're going to get that equation. The 1/2 that we see up here came from a power rule in calculus. That's exact. That shouldn't have error in it, right? That's why this has infinite sig figs. So I apologize if that's a little bit too fast. We'll come back to this later and do this exact problem again, so don't worry about that. That's why this has infinite sig figs. Good? Okay, hit that problem. Go. Talk to your neighbor as much as you want. Use the solutions. Get a computer, get a phone, whatever. It's 10 to the negative 1. So it's a little more fun in class if you have someone to commiserate with. So hopefully you can partner up, talk to them, and I'll erase the board and start walking around the room. And remember, if you get done with the problem early, look for another problem and just keep working. Get as much of your homework done as you can. Most of you, this is going to take a few minutes. So. If you're not sure, you can always just ask your neighbor, like, what did you get on this line? Or are you right? You can check in with your neighbor frequently just so you're less miserable. Like I said, I'll come around with that. I think it's nicer to be in class. Yeah, a lot better. Right? Even if I'm dinking around with that. Oh, let me get that. So, Alan. Oops. Oh, Isaac, could you let's see. Isaac, could I direct you to talk with Alan? You could send him a direct message too, I think. Is that cool? I'm talking to Isaac on Zoom here.
Yeah, that's fine. I already asked the question.
Oh, okay, cool. Yeah, so and then yeah, because I'm sometimes slow getting back to the computer with all the buttons. You know what I'm saying?
Yeah, that's fine. Thank
Okay.
you.
And it's also in Canvas too. I think I've listed all the crap in there that you need. Cool. All right. Something I guess I could tell you now too. Everybody. You got to have a scientific calculator for this course. So if you need to know one, right? No graphing calculators on test day, scientific calculators only. These two are pretty good. If you're wondering why, that's what's required for the engineering licensing exam. So I just use my calculator policy is the same as the engineering licensing exam policy. And I know not all of you are going to be engineers, and that probably is bad for some of you and maybe not fair, but I just had to pick something, and that's why I chose it. So if you need a calculator, I've got them. I'm going to start spinning around. So those of you on Zoom, aggressively talk with Alan here and say you could send him pictures or whatever you could do. Start working on that problem, look at the solutions, and you could talk to Alan while I'm circling the room in here. Alan, does that sound like a plan?
Sounds good to me.
Yep, okay. All right, so far so good? Yeah, what do you think? Okay, cool. And then if you want, just grab another one while I take another one off the list.
Oh, actually, already, almost halfway done.
Nice, nice. I love it. So far, so good.
Yeah, so,
Gonna go check out the answer.
yeah, it's on,
Yeah, Rob George said that comments look for the workbook and someone is. Let me know if you're gonna find it right away. Dave. Yeah. You're doing this work, you're doing all right? Okay. So far, so good? Oh, cool. What kind of solution already? Huh? Okay. Oh, laptop with bigger screen? Okay, you want to change your mind, just go grab it. Oh, do you have a screen or a laptop? You want it? Okay, you can bust it out if you want, or if you want a laptop, too. Grab it. That's right. Let's look at battery. I'll put it up. You keep working. Doing all right. Work on solution check. Yeah. Okay. Cool. Cool. Know where you're looking.
yeah,
So far, so good. Okay, good. So far, so good for you. Okay, cool. Okay, good. How about you? Oh, nice, nice, nice. Okay, cool.
Just gonna do the 15.
Right on, right on. Sounds great. All right. Okay, you guys know what time solutions? Good, yeah. All right. Looks like people are doing pretty well on this. That's good. That's what we want, right? This should be something that hopefully most of you could do, and if you can't do it, that's fine too. But in theory, if you took 110, this should be something you could do. Right. What were we supposed to solve for? I didn't even read. Oh, we're supposed to figure out delta x. Okay, yeah, so it's basically just, can you plug in numbers and follow the sig figs and use the prefixes and stuff, right? Or use the scientific notation. All right. At this point, how many of you would like more time, or was that enough time? If you would like more, well, I'm just going to give you one more minute and then we'll move on. Okay, I just want to make sure everybody has a chance to finish that up because I was yakking a little bit there. Okay, if you wanted to, you could do 115, or you could do one of the other ones on that page or anything. There's a fun joke in physics in problem 1.12. All right. 112 is my joke to you. Yeah, actually, that's the very next thing I was going to talk about. Prefixes and stuff, right? Yeah. So we'll review that in a minute. I'm kind of skipping around a little bit just to try and keep it moving. So usually we'll go more straight to it. So 10 to the minus 6th, and we'll find out that prefix. Got it. So that's what I'm doing there. And I was going to bring that up next. I was going to talk about engineering and scientific notation and prefix. Cool. Good. Oh, it's that one. No, the one that's in black. It's a document. It's like the one that's not a link. I spent all day looking for it too, and I put it up there. Like, where is it? Second page. There you go. Got it. All right. You doing all right? Oh, good. Okay. So far, so good. That one's a little bit trickier, right? You got to rearrange first, right?
I try to get the final for you and just
Yeah.
numbers.
That's the way to do it, right? All right, I like that. Good technique. That's a good approach. Nice job.
Yeah, it's just.
Okay. Did you get it?
Almost.
Flip the sign in front.
Yes.
Yeah, I throw in a lot of tricks, right? So, yeah, these problems are easy to you know you can do it, but like you gotta practice and make those screw ups now so that you don't screw it up on test day. So that's what we're trying to do. All right. What do you think? Get that? I think if you want a laptop, so it's a bigger screen, I'll bring it over.
Yes, please.
Then at the end of the day, you can just help me by putting it away. Cool? Yes. All right. All right. All right. So I know you've got the solution to this online. And what was the final solution? Wasn't it 22 or could somebody help me? What was the unrounded?
22 micrometers.
Yeah, but was it like 2, 1 like that?
2.1. Yeah.
Yeah. Okay. So this was the unrounded result and it was in the second column. Is that right? Or wait, no, it was
Number 7.
like that?
Yeah.
Okay, right. Okay, so this is where I wanted to pick up. So the answer should be delta x is equal to that, I believe. When you punch it all into your calculator, and notice the Sig Fig is right here. So this is equal to negative 2.2 times 10 to the negative 5th meters. Now, the next topic that I want to talk about is actually the differences between scientific and engineering notation. So if you have this number in your calculator, the easiest way to get this thing, did I ask for this in engineering notation? I did. So we haven't discussed this yet, but that's the next topic. So that was why I chose it. If I need to write this number in engineering notation, I literally am going to do, this is what I would do on test day, right? It'd be in my calculator already, negative 2.2, actually it'd probably be negative 2.17 E, negative 5, it'd be sitting there. And then what I could do is I could use the mode buttons on my calculator and just change it to engineering mode so that it spits it out right. What happens is engineering mode, the only allowed prefixes are -3, -6, -9, -12, or +3, +6. So it has to be to a 6. And what students and instructors and human beings are likely to do is you'll be like, wait, is this 22 times 10 to the -6? Or is it, I don't know. I don't know. Well, that's what it is. So it makes me weird. I don't know, but somebody might shift it the wrong way or something. I don't know what. But if you want to, you could literally just punch this into your calculator, press the mode button. And if you need to know how to do that, I'll show you in lab, or you can come up after class if you want to know. I'll show you how to do this. Again, you need a scientific calculator for test day, so you got to learn this trick. TI-36 Pro is most similar to most of your graphing calculators. So if you have a TI graphic calculator, just get this one. It's pretty damn good. Okay, and it's going to be for all your physics classes. They're going to require this. So, all right. You get something that looks like this when I change it to engineering mode, and I will re-explain that in a minute. But this could be understood or written more clearly using a prefix. And this is a good time to bring up this fact. Look at the back of your workbook. If you've got a hard copy, great. On the back of the workbook is essentially the exam equation sheet you will be given at the start of each exam. There might be a couple other things here and there, and I'll tell you more like as we get close. But if you look at the old practice exams, the first page of each test is an exam equation sheet that looks like this. I always get questions like, what do I need to memorize? Look, do you need to memorize the prefixes? No, they're on your equation sheet down here at the bottom. That's what I'm saying. What equations do you need to memorize? Anything that's not on here that you want to memorize. Okay, so this is kind of a pretty good set, so at least you're not having to memorize everything. You know what I'm saying? And hopefully this will take the edge off when you're studying. And what I recommend is on test day, if there's some equation you need to have on your test equation, I hand out the test, write it on the equation sheet right when you get your test. Like memorize it and spew it out right when you get it, okay? So, all right. Anyways, I could rewrite this as micro. All right. So that would be 22 micrometers or 22 microns, as they sometimes say. Now, when you look at it, I personally think this is a more pleasant thing to look at, just purely from aesthetics. And that's all that prefix is. Why would we waste time on something that's purely aesthetic? Well, think about it. If you're a scientist and you're watching somebody speak and they're giving a report and all the numbers look like this, and it's just a bunch of powers of 10, it's tiring constantly trying to think, wait a minute, oh, wait, oh yeah, this is 100 times smaller than that one. Ugh. It's harder to see the differences in numbers. It's fatiguing. People get annoyed with you and you're less likely to get hired when you do a job talk. So if you like this one, right? Why didn't I call this 98.7 milliseconds? It looks prettier. So we will discuss this type of skill more in lab, but it's important to look good. Case in point, let's go backwards to page, I think, 2 and 3. Nope. Page 4. Take a look at page 4. Right? On page 4 of the workbook, you will see a whole bunch of different prefixes and a bunch of columns of numbers, right? So you'll see 3 columns of numbers. And just in case somebody doesn't have one and they're looking online here, actually, I think I could do it this way. Oh, no, wait. Zooming and rooming takes a little bit of thought sometimes. So I apologize if I seem like I'm slow up here. You got to think about how things are going to show up in 2 modalities simultaneously. I don't want to spend all day on this, but like one of these numbers goes from all the way down to next one. I'll explain this in a second. This one. I think there's a couple extra zeros here. So when I look at this one, this column of numbers is written in scientific notation. This one is written in engineering notation. And this one is written in engineering notation with prefix. And when you look at large quantities of numbers side by side, it's like, this is just exhausting. I've got to focus on the power of E as well as the number here. This is not what I want to be doing. Right here, I have the same E value, but it's just fatiguing to read all that. This is definitely better. But then when you just see it all in the best choice of prefix, if things are all about a kilometer and you list them all in kilometers, it's a lot easier to see, oh, these numbers are just going from 1 to 500. And then the reader or whoever's watching you give a talk, they understand what you're talking about and they focus on what you want them to know rather than numbers. Okay? I don't know if that made any sense, but when you have to give a talk and you have to give 3 in this class during lab, you'll know what I mean. You want to make it look good, and we'll focus more on that at that time. So now I want to make sure you understand the distinction between scientific and engineering before we go on. And I'm just going to do it really quick because it doesn't take much time. Sorry if you already know it. Before I do that, are there any questions on this from Zoom or from anybody out here? Why do you do this? Because it makes you look good. And when you look good, people listen to you and give you more money. Okay. Something like that. All right. So now you can look at, have page 2 and 3 spread out like this in front of you. Page 2 and 3. Just hold it out like that. Yes, go ahead.
I mean, I was about to make a joke, but like, take a look at Apple, for example.
Uh-huh. Well,
All of the aesthetics.
yeah, right. People like it, even though it's more expensive because it's easier for them to work with, right? It's got that aesthetic appeal. So there's definitely something to that. Okay, so scientific notation in engineering. They're a little bit different, okay? So scientific, so let me give you an example here. I have a number here. This is one I wrote up. Let's say I have 0.000232215. And let's say this is seconds. Actually, that was, how about meters? Just let's keep it easy. Meters right now. So there's a number I have with some units. If I'm trying to convert this into scientific notation, I would go 1, 2, 3, 4, that direction. This would be 2.3215 times 10 to the minus 4th meters. Great. If I was doing this in engineering notation, can you see those markers on Zoom?
Yep.
Yep.
Right on, thanks. Geez, I hope I remember to hit the live stream button, did I? Yes. Whew. All right. When I'm doing this in engineering mode, the only difference is this: go by groups of 3. Okay, so 1, 2, 3. I'm not over into the significant digits yet. I have to go another 3. I can't just stop at 1. 1, 2, 3. So let's see here. So what would that be? Did I move this? Did I write down the number wrong? No. Okay, it's just a weird one. Yeah. So this would be, well, what you tell me, what would it be? It looks a little weird because it's not the same as scientific, but in this case, what would it be? How many did I go over? 6. So I have to do 10 to the minus 6. If I go 10 to the minus 6, what's the number that's left?
232.15.
And then if I was going prefixes, what happens to this right here? It's a micro. That's going to go to a mu. All right. So this is the old school way of doing scientific and engineering. What's the best way to do it on test day? Remind me. Change the modes in your calculator, right? If you don't know how to do that, get your scientific calculator soon so I can help you learn how to do that before test day. That's like easy points. You don't want to lose them. All right. If you need more practice with this, there's tons of practice on page 2, page 3. You know, and so if you're really good at this stuff, a fun one was problem number 5, right? So there's some weird physics units in problem number 5, and you might be wondering, what's a BQ? Or what's a BEL? Or what's a CD, right? So I put in a bunch of weird units, and then if you're having fun, you can look up what those units mean in the answer key, just for giggles. All right. All right. Let's just get thumbs up, thumbs down. How are you feeling on scientific versus engineering notation? Okay, most people pretty good. All right, thanks for your patience on that then. Okay, so you can do those problems as you need to. I've done this. Let's see, we started at 4:30, and that clock is an hour off, right? Yes. Okay, so we're doing all right. We're almost an hour in, is that right? Okay. I will give you a break in a couple of minutes. Don't worry. I want to talk about unit conversions real quick. I want to try and blast through as much as we can. So look at pages 8 and 9 while I get the board erased. And if you want to, you can look at the examples on page 9. So again, I'm just going to erase the board. Those of you on Zoom, just look at pages 8 and 9, and there's a couple of examples there. Take a look at those real quick. Okay. Pretty boring stuff, isn't it? But necessary, not very exciting. I'll try and burn something or blow something up at the end of the class today, all right? Let's see what we can do. On this board right here, wait, I'm on the wrong board. All right, so unit conversions, all right? I know you know how to do this, but let's just look at, let's look at 1.18. And let's do 1.18 C. Just to see what's up here. 1.18 C. In particular, 1.18 C asks us to convert $495,000 or 49,500, excuse me, feet per hour squared over to meters and seconds. Engineering notation. Best prefix. What's the fastest way to do this? Google, right? Do you agree? But you don't get to use Google on your test. You're probably going to get at least one question like this. And it takes a lot of work, but I was able to find one or two unit conversions Google had yet to figure out. They're really hard to find these days, but yeah. So obviously in the real world, you would use Google, but we also want to know how to do this just because it's good to check. And sometimes there's a weird situation where you might make up your own units and need to know how to convert them. So let's learn the old school way. Any advice from anybody? What would you do?
I would start up with feet.
What do you mean by that?
So pretty much, we're supposed to convert 1 foot to 12 inches.
Okay. So how do I go about doing that?
So dividing.
Yeah, that's
by
right.
1 foot. And then
Okay, I
multiply
divide by a foot and multiply by, yes, exactly. And so if you're not used to this, this is the other thing chemistry was good at, doing unit conversions. I call this the railroad tracks, where you're just gonna pile up the units. Absolutely, good. What was next?
And then divide by 1 inch.
Okay, it goes,
And then multiply by 2.54 centimeters.
yeah. And that's gonna get us to centimeters. Okay, so then from there, somebody else, what's the next step? Well, when you look at this, we've gotten rid of the feet. We've gotten rid of the inches.
Yeah, 100 centimeters.
Yeah, exactly. So we got 100 centimeters is 1 meter. Alternatively, somebody else might say it this way, 10 to the -2 meters is 1 centimeter. Do you agree that's the same conversion? So if you forget what these prefixes are, you can always look up the prefixes on the exam equation sheet. So it's not having to remember everything, right? If you forget these, use the prefixes on the exam equation sheet. All right, so that's going to get our centimeters taken care of. Then what? How many seconds in an hour? This is one maybe you don't know, but you'll have memorized in a week. Or it's on the equation sheet. 60 squared, right? 60 minutes times 60, 3,600. Whoops, wrong spot, isn't it? What goes on top in this case? Hours or seconds? I need the hours to go on top because in the original, oh, shoot. So 1 hour is 3,600 seconds. Now it's going to work out, right? Ah, what did I forget?
To square the hour and the seconds.
I forgot to square it. So if you have to square this, you have to square this and this, but if you have to square this and this, you must also remember to square the numbers. So don't forget to square those numbers. You know what I'm saying?
Good trick is just parenthesize the number and the unit itself.
You can absolutely do that too. Like he said right here, you could just square them both. And when you do that, just make sure you remember to square the number. All right. So from there, go ahead, punch it out. What'd you get? Did somebody get it already? I'll do it as well. So now I'd say 49500 I'm just going to do all the multiplies first and then all the divides. So I'm going to multiply by 12, multiply by 2.54. 1 squared is still 1. So then I'm going to divide by 1, divide by 1, divide by 100. Then I'm going to divide by 3,600 squared. And so out of all that, I got 1.1642 times 10 to the minus 3, because my calculator is in engineering mode already. So that's the trick. If you know you want your answer in engineering mode, just change your calculator to engineering mode while you're writing the calculation. How many sig figs? This is a tricky one. All right, let's talk about this. How many sig figs do you think we should have? Why do you say 3?
The number that matters is the one that they give you.
Usually. Almost always, the only one that matters is this. Do you agree that this one has 1, 2, 3 sig figs? Now, look at this. Wait a minute. 12, doesn't that only have 2 sig figs? But there's exactly 12 inches in a foot. This is an exact calculation. Physics or national standards and institutes have said exactly 2.54 centimeters in 1 inch. And in fact, look at the top of page 9. All of these are exact unless you see an underline. Do you see like the first one? If a conversion was not exact, I would tell you. This conversion is only good to 4 sig figs. These ones are good to infinite sig figs. So that's another thing you got to watch out for when doing sig figs. Did that make any sense at all, or questions on that? Okay, so, and where are you going to find the most common conversions? Right there at the top on your exam equation sheet. You can double check if you don't believe it, right? So you're going to get that. If you're curious, wait, what's the formula for a circle and all that stuff, right? A lot of these formulas that you see here, a lot of those are up here. Okay, like the quadratic formula, we use that at least once or twice on a test. So yeah. All right. Feeling good on that? All right. And to be honest, I'm not going to try to mess with you on this one on test day, right? So generally speaking, let's stick with this. 3 sig figs right here. What was the final answer though? I forgot.
It was 1.16
What are the units? What are the units that are left over?
millimeters per second squared.
Okay. That hour is going to drop out there. So this was, yes, this was right here. This is still meters per second squared. Agreed? So what we can do, and I think what he said is, why don't I just take this 10 to the minus 3 and make that millimeters per second squared. And just to show you how annoying physics and engineering can be, this is one where oftentimes engineers would make an exception and include 4. Don't blame me. I just work here. But yeah, work, right? So I'll explain more about that. When you start doing homework, you'll see that sometimes what happens is engineers will take numbers that start with the digit 1, numbers whose first digit is 1, they add a sig fig. And that's complicated error analysis. I could explain it to you after class if you care. If you ended up doing that on a test on this question, I would probably mark you wrong. So for this type of question where I say answer it using correct sig figs, there's usually only one test question in the whole semester where I make you do that right. So there it is, that kind of thing. I'd say like, look, I said do it right, do it right. All right. Feeling okay on conversions right now? Kind of a good reminder of what's up there. All right. Let's do one more thing really quick, and then we'll take a break. One last one. Let's go to board 6. Density. We're going to use the symbol rho, not D. So it turns out we use diameter a lot for D and distance is D. So we don't want to keep using D all the time. So we're going to use this. Greek letter rho. Rho your density. So now density is mass per unit volume. Now I would like to point out, really, what we're going to use density is, it's kind of like a special conversion between mass and volume. Let me show you what I mean. If you rearrange this equation for mass, what does it say? Mass is equal to what? Density, rho, times volume, right? So if you know the volume, you can convert to mass. So think of this density in some sense like a conversion factor, right? Or we could go the other way. If you want the volume and you know the mass, what do you have to do? Volume equals, rearrange it, divided by, yeah. So we could see that you could use density to convert mass to volume or volume to mass, understood? So that's all I wanted to say before your break. And if you don't know how to draw this symbol, just watch one last time. You start right here at the crux of the P, and you swivel it down. You do not want to write a P. Okay, that's wrong. So rho means density. P means momentum. Capital P means pressure. Oh my gosh. In this class, we have lots of different letters. And notice how I'm using a capital V for volume. You're going to notice me doing this a lot because what's lowercase v in physics? What did we see earlier? Velocity. Velocity. Right? And then, okay, so we're going to start reusing the Greek letters by the time you finish this class. It's depressing. But yeah, if you're not sure about a letter, just ask anything like that. Let's take a quick break. Try not to make it too long. So let's just try and get back at 5:10, okay? So those of you on Zoom, any questions out there? You surviving there? Okay, and remember, you can always talk to Alan directly. He knows everything. All right, I'll stop the video for a second, and we'll come back in about, I don't know, a couple of minutes here. Just going to be erasing the board, those of you on Zoom. We still got another minute or two. All right, all right.
Oh, and I do have a question for the
Sure.
homework checks. Would you like for us to draw the pictures?
Oh,
of-
I'm not doing homework checks. No homework checks. You may have printed out the old one. I printed a new one of those.
This
Yeah.
was a new one.
Yeah, yeah. So I'm not going to check any of the homework at all, ever.
Oh,
It's just you do it your own way, and that way we don't have to deal with that. The only reason I did homework checks was when it was online as Canvas. And I was trying to give people points for doing it, but
okay.
when we're in person, I don't have any of that. So is that answer that one?
Yeah.
Yeah, so there's not gonna be any checking of the homework. It's just do it to learn. Got it?
Got it.
I do recommend that you at least do some of them and try to be neat. Otherwise, you go on to the engineering classes and you haven't been in the habit of trying to be neat with your work. And if at any time you want me to critique your work, or I'll tell you as I walk around it occasionally, you should try to work neatly, but I'm not going to actually check your work for homework. It's just tests, labs, and that's it. All right. Good question. Good question. All right. So hopefully, right now, you kind of feel like maybe you know most of what we've been talking about. So let's go to page 11 and see if we can put this all together. 1.26, you should maybe circle that problem. If you have any trouble with what we're about to do, make sure you do problem 1.26 like today or tomorrow, okay? That said, I want to do 1.30 right now. Again, if you suck at this and you need extra practice, immediately after class, go back and do 1.26. All right, because that one's got a super detailed solution with every step and all this, right? So that's why I'm saving that for you to do at home, because I know the solutions are pretty bomb for that, all right? So let's look at 1.30 right now, because it's also telling a story. Am I on the right Zoom board? Yes. 1.30. Imagine you have a little drop of oil. Okay. And then it's going to spread out into a giant pancake. And that pancake happens to be a perfect cylinder. This is my attempt to draw that. I don't know if that makes sense, but hopefully this. So the idea is if you drop some oil on the surface of water, it's going to spread out like this. Is everybody okay with that? It's going to make an oil slick. And for now, let's just assume it's a cylindrical. All right. So, and let's see. And then, oh, I don't think I mentioned this. So the volume of the oil that I'm going to use is 0.5 microliters. You might be saying, what? How big is that? So this is what's called a micropipetter, right? And the drop of oil, if you have like a ballpoint pen, it's going to be probably smaller than the ball of the ballpoint pen, but about that size. You know what I'm talking about? How those pens have a little ball in it? So I can't really show it to you that easily, but it's going to be a tiny little drop, basically like the end of that little piece of plastic there. So it's so small you can't see it. All right. Yeah. basically tinier than the very tip of this pen. Something so small you can't really see, all right? Or not very easily unless you get up close. So from here, what was I doing? Where's my book? Where did I put it? Oh, there it is. I got the pipetter. I'm gonna lose that too. Let's put that back. Okay. How would we get the diameter of the drop? What would be a good procedure? What would you do? Any thoughts on what you might try? I'll give you a minute to think. Talk with your neighbors. I'll start going around. All right. And then the next part is
D squared. And then that way we can rearrange the, we can algebraically this equation. So that we can, plug in for, have you seen calculus?
maybe I'll call that D subscript sphere, because do you agree there's two diameters here? So
I could be wrong.
okay. What do you think? Any ideas?
Actually, I didn't need to write them down. Absolutely. Then also, what's the other? D squared.
You're gonna have to convert. Right? Okay, so that's okay.
So let me solve this out.
Can you write it down?
Sorry.
One C.
By the way, if it helps, does anybody know how liters relates to meters in any way, any unit? Like, have you heard that 1 cc is 1 milliliter? So this means 1 centimeter cubed is the same thing as a milliliter. If that helps, right, this is probably something you would Google in the real world, like convert 0.5 microliters to meters cubed or something. And you could do that right now if you want, but if you wanted practice with your conversions, that will help. All right, keep going, keep going. And remember, on Zoom, if you're like getting broken by this or frustrated, remember, you can talk to Alan. How are you doing, Alan? Are you getting any questions right now or not really?
Not really. I did get one in the beginning, but that's about it.
Yeah, exactly. And I understand people on Zoom. It's like you might be doing your own groove or taking practice tests right now or something, and I understand. So hopefully, maybe next class, or even, or at the latest next week, hopefully this Omicron will be kind of dissipated and it won't be so stressful for you. And then I recommend everybody coming to class. It's just more fun, I think, in class, but with Omicron, it's kind of like, and this stuff, who cares? But all right, anyways, that's what I'm thinking about you on Zoom, and hopefully you're still having a little bit of fun today, or at least getting some work done. All right. Okay. I'm gonna go around the room here. If you guys have questions, talk to Alan. All right, Alan, just hang in there. Alan, if you are you able to access the Canvas course, Alan?
Yeah, I'm on it right now, actually.
Yeah, so what you might do then is kind of skim through the lab and remind yourself what's going on if you're not getting any questions. That way you're not wasting your time. You know what I'm saying?
Yeah, sounds good.
Kind of remind yourself of vectors and all that crap. And yeah.
Yeah,
right.
all right.
All right, Alan, you're the man. Okay. I'll start here. So far, so good. Got some ideas. Yeah, it's good. And then, I mean, just because you guys happen to be sitting next to each other, like if you bounce ideas off each other, it's sometimes more fun. You just feel less desperately bored and fatigued and alone and miserable. So like if you want to, you can bounce ideas off him and vice versa. And then you can all be working on your own stuff. So just letting you know that. You're doing all right too?
Yeah, that's exactly what we're doing.
Okay, cool. Yeah.
This is what I came up with.
And if you get done early, try and finish the whole problem.
This is what I came up with. No, I didn't really like this.
No, I think that's, let's see, so what are we gonna say? It's gonna be pi, oh yeah, pi over 4 diameter of t, and then we gotta rearrange that for piece of 4v over pi t. Yep, yeah, that's it. Go ahead, there's a number there. Yeah.
Perfect, thank you.
Yeah, that.
By the way, this diameter of this,
The cylinder.
we're gonna assume that's gonna turn out to be about 60 centimeters, and it's gonna be good to just one Sig Fig. I just wish there was a way we could have an oil slick in class. Ladies and gentlemen, Angus Lewis. Let's give him a round of applause here. But we're gonna try and do the demo in a minute. So get the calculation done, hurry, so we can actually do this. This is like the closest thing I can get to making this exciting in class. While you're doing that, I'm gonna prep the camera on Zoom, all right? Oops. Wrong way. Alan, I don't think you saw this one, did you?
No, we didn't.
That's right. We were all in COVID hell back then. Is there a way I could get you guys to scoot down just so I could move this table so that the camera can see down there? Like just scoot down that way one seat? Is that I think it's hitting your laptop and stuff too. That'll help me focus on the oil slick.
Do you need to?
Actually, I might need to turn that right angle. I think that's what I'm seeing. What are you seeing? Oh no, it's getting you. Yeah, so that camera's getting you. Is there a way you could maybe scoot one more, or if you want to just jump back there if you like to practice? Let me see if that gets it now. Hey, there we go.
I got so I got 4.42 something.
I can see it a little bit. I think that it's not going to be perfect, but it's going to be better than the last one by far. I think we can see it. Okay. And while you're doing that, I'm gonna do this part.
That's how much that is.
So for those of you on Zoom, I'm just bringing up the solution so you can see what they're seeing as well. Again, if I want to find a problem quickly, I just open it, hit Control F, and then we're on what, 1.30? And then I'll make this a little bigger.
60, so 60.
All right. So there's the solution, just so you got it. So if you're on Zoom looking for it, you can do that. Just let me check. How are people doing in class? Are you making progress on this? Are you about done? You need a little more time? Just be straight with me. Do you need more time or not? A little bit more? Okay, okay. Okay, so I'll make sure you got the solutions there on Zoom. I'm going to come around the classroom real quick. All right, getting somewhere or not? What's that? Not sure. Okay, so this is this should be square. D over 2.
So we would be using a cylinder.
That's good. 4.
It's not asking you to stand.
Remember, you got the solution, right?
Yeah.
Okay, good.
Equation effect.
Get somewhere? It feels so weird because it's so rare that we actually do that conversion. What I would do is I would go to liters, right? And then go to milliliters, just so I don't screw up the 10 to the minus 6 and 10 to the minus 3. Or you could just do a 10 to the minus 3 like you did, and then double check that it makes sense when you back convert. That's right, so that's gotta be in meters. So then I gotta go from milliliters to centimeters, because that's what I know. So 1 milliliter is 1 centimeter cubed. And that makes sense, right? Because the volume should be meters on meters on meters. So that's good. And then from centimeters, you could go to meters or milliliters.
You understand this transition?
Yes, yes, yeah. Well, so the volume should stay in the cube. So what I would do is, right, I would actually get it to centimeters and then go from centimeters cubed to meters cubed. And then the volume will be in meters cubed. And this is the trick that you want to do, is basically get everything into some normal units so you don't screw it up. Then do whatever you want with all of them. What happens is, somebody is pretty smart. And they can kind of do it, and most of the time they can do it in their head. Right? And that one time you do it in your head and don't double check it, is when it's on the test. Right? So sometimes just doing the slow way. And again, this is where in the real world, Google would be nice. You just punch it. So, okay, good enough on that? Yeah. All right, good thought. Good thought.
Question.
Comment?
So, is it asking in engineering or scientific notation for,
I forget.
for C? Didn't specify.
Yeah, just pick a notation.
Okay.
One of those two is good. So if I don't specify any notation, is legal.
Okay, thank you.
Yeah. How about here? All right.
Yeah.
I think I put it in intro here and go see if it's care. Yeah, it's funny, right? It's like a weird question, and you're like, oh, that's it? But it's weird how it's written for some reason.
Yeah, I thought.
Yeah, all right, that's cool. But you're on track now.
Yeah.
There you. Yeah, and that's what the solutions are for. And what happens is, I write all these. I also write all your test questions. You'll get used to the way I talk. So then I'm testing it, you're less likely to easy by someone say.
Yeah.
So.
Conversions, right? Yeah. Yeah. Yeah, well, a lot of times what I find is it's better to just get all your conversions into one set of units at the beginning and then roll. And I've seen this happen in lab too, where if you try to not do that, it's close. Okay, cool. What do you think? You doing all right? Yep. Okay, yeah, it's funny, there's very few numbers, right? You need the volume and the diameter, and you get the thickness. Think about this, in a minute, when we do the experiment live, you can actually see or use the dimensions we can measure with rulers to figure out the size of a molecule. That's crazy, right? All right, yeah, how about you? You're doing all right? Looks like you're good, right? Oh, the Sig Figs? I gave you one. So in this one, we're only gonna be good to one. Because it turns out when I use the micropipetter, it's really hard for me to do. That's the smallest increment, so it's only 1 Sig Fig. And then you'll see when we do the experiment, it's a real big blob. So it's hard to get the centimeters exact. So yeah, this is only giving us an order of magnitude, just 1 Sig Fig. Yeah. Is that good?
So for example, that's really 0.1.
What's that?
That's really 0.1 or 0.3.
Well, that would be wrong because it's gotta have units. So it might be 0.1, but I don't know what units you're talking about. You see what I'm saying? So it's crucial that you have units on your numbers. Otherwise, it's like immediately wrong. Right, you could be right, you could be totally wrong. I have no idea. All right. So double check the solution. I got it. I'll be right up there. I want to get one circle through here real quick. You're good? You have an idea what to do? All right, good. You're making progress?
So I thought I got this wrong, but then when I looked at solutions, it was like
Oh,
set to
well,
negative.
once you get rid of it.
But I got like negative.
And then the volume is it, I would convert the volume to meters.
It's in meters.
You see what I'm saying?
Yeah,
Yeah, it's like, is this a weird one? It's like, who uses
Whether
weird?
it's like,
Well, it turns out a lot of people use it. I think I might have to pay my son. So that's just fine. Is that good? Okay. And watch out, that's not a milliliter. It's a micro. See the difference in the averages? The volume's oil, there's not, and the 1 cc.
like tea on that, it's like top.
Right, so you gotta watch your end. On the Greek letter M, that's just, got it? Progress? Making progress? Okay. Sorry about that.
No worries.
You get it figured out or not?
I did actually.
Ah!
No, well, thing is, I thought I did this wrong because I was looking at the solution and it was, 2 times 10 to the negative 7 centimeters.
Centimeters,
Yeah, but I thought
which
it
is
was
gonna be 2 times 10 to the minus 9 meters.
That's what I forgot because centimeters is
Yeah,
pretty
yeah.
much.
Yeah.
10 to
So think about that too. This is like getting close to the size of a hydrogen atom, right? We're measuring things that are right, so we're gonna be measuring something that's close to the size of a single atom. It's going to be a single molecule of oil. That's crazy. All right, so tell you what. Gonna stop that share for a second. So Zoomers, this is the interesting part. I hope you can see this. Class, you could come up here in a minute if you want. We'll try to keep this line of sight so that the Zoom might see. So if you want to come up and take a look at this, that's cool. If you want to just, right, so here's some lycopodium powder. Has anybody ever heard of lycopodium powder before? It's just moss spores, right? So it's gonna be more fun if you get up and walk around the classroom. Just do it, make me happy. It's really hard to make Sig Figs interesting. I'm trying my best, people. So we could roll this part out of the way. What I could do is I could move this part back this way, right? Let's do that, yeah. Then we kind of see it a little bit. And then once you get situated, I'll see if anybody needs to move out of the way. Oh, you're right in the camera. So right where you are. Whoops, you got to move. You're right in the camera. Here, just come up to here, right here. That'll be work. Yeah, and then if somebody else wants to come up here, they can do that. All right, so. Whoops, just lost my micro pipetter. Let's get this. Okay. There's still enough oil in there. Nope. You can see I've already screwed up the Sig Figs on the oil drop. If you're a biologist, my apologies. If you're on Zoom, just give me a sec. And you can barely see it anyways. But is there a meter stick laying around somewhere?
Right behind you.
There's one too. Oh, right there. Thank you. All right. So again, this is a tiny drop of oil. You can almost see it there. And so when I drop this on here, get it to drop off. It's spreading out. And actually, this is looking about right. So let's see what 60 centimeters is. That's about 60. And what happens is over the next half hour, it's going to slowly creep out wider. And so you can see, I'm not making this crap up. This is about a 60 centimeters diameter. It's not a perfect cylinder, is it? That's why 1 Sig Fig is appropriate here, right? We could be off by quite a bit. So that's all I got for you for a demo today, but it's better than nothing, right? So this is the problem you just worked on. If you read the little paragraph right afterwards, it's slightly interesting. It's a sad story about Agnes Pockel, and right, she did all this work and had to get other people to publish it for her. She eventually got it out, which is cool. But she made some device which was related to this in her kitchen, and it was like precursor to the Engr trough, which is still used today. Very interesting stuff. Does anybody know anything else about lycopodium powder? Well, I do. Go ahead and grab your seats, and I'll tell you one more thing that has nothing to do with Sig Figs. Let me see what this does. Let me Zoom. Up. Up. So this is just your chance to veg out for a little bit. Might as well have a little bit of fun. Lycopodium is lycopodium powder is moss spores. Right, so it's just moss spores, and I have some right here. I'm gonna put it on this plate. Okay. Now, I like this little. Can you see me on Zoom or not?
Yeah, we can.
Okay, thanks. Got a little burner here. And just to show you here, this stuff is not very flammable, right? But this is a chemistry demonstration usually, but if I'm gonna waste my time getting out lycopodium powder, I'm gonna do this. So just so you're aware, I'm gonna take a really deep breath and blow this lycopodium powder all over the place. So if you're worried about that with COVID, I'm not offended if you wanna leave the room or anything. But it should be fine with this volume of air. Okay. So turns out, if you get the right fuel air mixture, let's see what happens. All right. Now the trick, if you're going to do this, is twofold. Number one, you got to manage to not blow out the flame. And number two, you got to take the deep breath before you put your mouth on the hose. Otherwise, you basically huff a bunch of lycopodium spores. Ready? One. Oh, I got my eyebrows. Yep. Good thing you got a mask. You won't smell all that burning flesh. Okay. Isn't that kind of fun?
Yeah.
Hopefully I didn't get you. All right. I was doing the math in my head. I didn't think you did that. What am I doing? I was playing with the lights now? Whatever. I think we're good. It's kind of interesting, right? What do you think? Did Angus do a good job? What do you think? Let's give out a shout for Angus. Woo! He's underpaid and overworked, so all he gets is a couple of claps once in a while. All right, so I know maybe some of you, what's that? Oh, I just said, nice job. I said you're overworked and underpaid, so all you get is a couple of claps once in a while. All right. Oh man, yeah, I definitely got some eyebrows there. All right, where were we? Let's go back to just to keep you awake there. All right, I know maybe some of you didn't get through 130. That was kind of a fun problem. I just wanted to wake you up. Go back and do 1.26 at home tonight. And if you're, feeling pretty good, you can see this. I like to ask questions like this where there's objects with holes in them. Here's why. It requires a subtraction and it requires you to pay close attention to Sig Fig rules. You see what I'm saying? So if you do a couple more of these, as soon as they get really obvious and boring to you, stop and move on to the next thing. So what do we got? 10 more minutes, right? Or no, wait. What is I forget the official end time today. Let me look at it. Does anybody know it? What was it? 6:45? So we've got 25 minutes. That's pretty cool. We're doing all right. Huh. Yeah, there's some fun ones in here. Let's look at page 13 now. All right. So I want to talk about dimensional analysis. And then maybe we'll even get out early here. I'm trying to cover all of chapter 1 at a super fast level. I realize it's super rushed, and let me get on the right whiteboard. All right, dimensional analysis. Sometimes you'll hear me call it unit analysis or check the units. I know it seems stupid, but it's something you should get in the habit of doing all the time. Okay. Maybe you don't know what I mean here, and so that's why we're talking about this as a group. Okay. I am a very picky person when it comes to reports and everything, especially on the subject of italics. I know. The proper use of italics means something to a scientist. For example, imagine if this was in italics. It's really hard to write on a whiteboard like this. These have
to be left-handed.
What's that?
Or just pretend to be left-handed.
Yeah, there we go. I'll work on that. So let's say this M was not italics and this M was in italics, all right? What does an M mean when it's not italicized? Versus when it is italicized. What does it mean to you? It's okay if it, yeah. What up, Dom? Hey, everybody, that's Dom back there. So does anybody, it's okay if you don't remember, but what does M mean to you when it's not italicized versus italicized? Yeah, go ahead.
Non-italicized is meters and italicized is kilogram or like mass.
Mass, that's it. So this is just one example of how the italics that you might use in a report or that I might use in a test question, right? That's probably what matters more to you. If I use an M in a test question that's not italicized, I'm implying units of meters. If I write it in italics, I mean the variable mass. If you're not sure on test day, what could you do to clarify that? Raise your hand and ask. On test days, you guys are used to being so smart, you know everything. It's okay to ask a clarification question during the test. Be like, did you mean mass here or meters? Worst thing that happens is I can't tell you that. I expect you to know, but usually I'll just explain it. If it doesn't give the answer away, I'll just tell you. So don't be shy about asking, or if you see something and you're worried that it's italicized when it shouldn't be, or vice versa, that's kind of on you to say, you got to raise your hand once in a while, right? Okay, there's one thing. But now, so in some of this work here, you're also going to see some other things here. Sometimes you'll see a capital M like this, and I'm looking at the top of page 13. This one, again, top of page 13 in the workbook here. Some books will use that symbol for the dimensions of mass. Other books, or your instructor, me, and a lot of people you talk to will just say, oh, it's kilograms. So notice this is a unit of mass. Take a guess. Do you think that kilogram should be italicized or not italicized based on your life experience?
Not italicized.
Not italicized. Units are not italicized. So that's, and I will remind you of this in lab. That's usually where we address this. But just so you know, units, generally speaking, are never italicized, and variables are. This is a variable. Okay. So more on that throughout the semester as we go on. This term with these square brackets means this capital M inside of there is another notation used by a lot of the most famous physics books to indicate that. However, usually in all my solutions, I just write kilograms. That's just the style I grew up with. What do you use, Dom? Units or the dimensions of, or do you rarely do this probably?
I use units.
Yeah, a lot
I
of
actually use units. If I'm just talking about units, I put them actually in square brackets.
Oh, interesting.
Just so that I'm saying this is not part of a problem with numbers. I'm just thinking about the units.
Yes, and actually that's one of the things that we're about to do too. So I hope that my style is the same as yours, and I guess that's one of the things we'll find out in a minute. So that's actually why Dom's here. If you guys don't know, Dom is the engineering instructor, math chair, super good instructor. And I'll say this right now on the record. If you have to, like, if Dom tells you something and I tell you something, I would listen to what Dom has to say over me, right? He's published through a real publisher. I just do Amazon, right? So he knows his stuff very thoroughly, all right? So if there's ever a question, we can always ask Dom. He can make a suggestion, and there's nuances, but whatever. So yeah, great resource to have that he's able to occasionally drop by. All right, where was I going with this? Let's do a problem, all right? Oh, I should mention this. There's a handout online. So right below this, I just want to point out, if I'm doing a bad job explaining this, because I got distracted there and got off my script, I want to point out, see those 3 asterisks right there on page 13? And this might not be in the online version of the workbook because I haven't updated the online since a while. But basically, right next to the chapter 1 solutions, if you've got your chapter 1 solutions up, look in the rightmost column on that website, and you should see a handout that Vince Tobin made that's really well done as well. All right. So, okay. All right. There's a few other notes there. I'll maybe summarize the big part out of this. For me, let's say this is M that's italicized, which means mass. In my book, what I try to do to keep this straight is I will say this symbol around that is this. So, and this might be different than how Dom does it, but I say the units of the variable inside are kilograms. So that's the notation that I use. And that's how I guess I grew up with it. The units of the variable mass are kilograms. So I like to have the brackets around the variables. And then once I tell you the units of those, the brackets go away. And it sounded like you keep the brackets around the kilograms. Is that correct, Dom?
Yeah, because it's more of a dimension type check.
Yep. So you might be saying, why would anybody ever care about this silly little stuff? Well, I argue it can help you check your work and reduce the amount of time you have to spend listening to me. All right, you'll pass my class and never have to see me again. So let me give you an example here. Let's look at 1.33, and I'm going to erase this board and do it over here. 1.33. And I'll change the whiteboard in a second. Zoom. All right. I change the whiteboard on Zoom right now. Maybe. There it goes. 1.33. Maybe let me do this really quick. If you want, you could try and stumble through it on your own right now. I'm just gonna really quick. You could, right, maybe there's some notes in there that you'd like, oh, you should clarify it this way instead, right? Okay. Does anybody happen to know what this equation means by chance? This wasn't a physics equation that we're going to learn about much later. Does anybody happen to know it just for fun? What does K mean? You know? You should know this. Okay, some of you that had high school physics maybe have heard kinetic energy. So this is 1/2 mv squared, mass times speed squared times a half gives you what's called kinetic energy. So if you knew the mass of a baseball and how fast it's going, you would know how much energy it had in terms of kinetic energy, whatever. All right, so what I want to do is, sometimes you'll see me say it like this: what are the dimensions of K? Or determine units for K. All right, so let me show you how I would do that and explain how all that stuff I just said relates to this type of problem which shows up on a test. What I do is I put these square brackets around them like this. Now keep in mind, according to what I just told you, what does this set of symbols mean? It means the units appropriate for K, the variable. and maybe I'll even say that, for the variable. K. Right? This would be the units of variable M. This would be units of variable V. Now, just in case you don't know what these are, I'm going to write this as mass, right? As time goes on, we'll start to learn more of these. Maybe you didn't know this, but V is equal to speed, not velocity. Sometimes it'll be velocity. What does this mean? Tell me what you think this,
That's just a constant.
it's a constant, true. What does this mean with the brackets on it? What do the brackets mean for everything? The units of that constant, right? So this means the units of 1/2 the constant. What units are on 1/2 in this equation? Do you see any units? Yes or no? No units. So this one has no units. Now this is tricky. It's not the same thing as 0, right? In math, if something was 0, right, 0 times something else would equal 0. Here, no units times something with units, the no units phrase just disappears. You might have seen this already in a calculus class if you talked about radians, right? Maybe you remember that radians times anything else, the radians can get absorbed. I don't know if they did that or not. If not, we'll do it in here. But let's finish this problem. Okay, so really what's going to happen is we would have no units times, what are the units of the variable mass? Remind me. You could be grams, sure. Usually we pick the standard of kilograms, but you'd be right. You could have said grams and I would have taken that on test 8. But usually we choose kilograms, meters, seconds instead of other stuff. Some old systems used centimeters and grams and seconds. That was the CGS second. Now we're going to use this, what's that called? SI or whatever. Okay, how about this term?
Meters per second.
Okay. Everybody feeling good on that? Let me rephrase. Why is that wrong? Squared, right? See that squared? Ah, the equation had a squared in it. Ah, what do you think that does to the units? Squares them. Got it? And so in this case, this is my style of doing it, and we already know it's not a standard style. It's one style. Okay, fine. It will, right, the rest of the brackets, you could learn that based off each teacher, how each teacher wants to do the brackets. But let's clean this up. There's one last piece to do here. No units times something with units. The no units disappears. So I could write this cleanly as a kilogram meter squared per second squared. And then what happens is students get lazy and they don't think the bullet is important here. Well, I'll just take off some points if that's fine. Right? Because there's a difference between writing KGM and KGM. They're not the same. So this is one of the unpleasant realities of doing science. Everything you say is taken at face value, so you'd better say it right. You got to be neat. I wish it wasn't this way, but I mean, Dom, I mean, what do you think about what I'm saying now? Am I lying to you?
No, it's good. It needs to be
Precise.
clear and correct and unambiguous.
Yeah, so
KGM means nothing.
yeah, I don't know what that means. So then I'm like, okay, this person doesn't know what they're talking about, or
This is kilograms times meter. That's what that last thing we wrote says. taking something that's mass and we're multiplying it by something that's thick.
By the way, Alan, on Zoom, can you hear Dom when he speaks or not?
Just slightly.
Okay, so I'll reiterate that to the class. So yeah, basically Dom was saying that this clearly states you have kilograms times meters, as opposed to here, we're not sure, like as scientists, what this means. And if we don't know, we get confused. And if we're confused, we waste time. And then we don't want to waste time. Dom, I don't think I paraphrased that very well, but sorry. Good enough for now.
Time's our most precious resource.
Waste everything except time. Okay, feeling okay on this? By the way, this is a real gem of a unit. It has another name. It's called a joule. The jokes don't work in a mask, but I'm going to tell them anyways. I don't care. Okay, a real gem of a unit. Anyways, all right. I wouldn't expect you to know this last part yet. Okay, where are we? 6:38. Good. We got 7 minutes. How about we take this time to try any problems you want between 1.33 ABCD and 1.34. Okay. Or you know what? Those ones, you know what? I take it back. I want to show you one other way this can be really useful, and it may surprise you that somehow this might be useful. So let me try another question. Let's try a hard one. Page 14. Let's try medium hard. 1.37. So I'm going to do 1.37 on Zoom. I'm going to fix up the boards just a second. 6. Okay, 1.37. And the reason I'm picking that is this is going to be kind of confusing, but you've got a handout. One of the tricky things about college, you have to do 80% of the work on your own, and we only cover 20% in class. Have you heard that rule before? In high school, it's 80-20 the other way. High school, 80% is in class. So you're going to have to do some work on your own. And this is, right? I'm trying to pick the problems that are nastier in class. That way I can help you on those live rather than you struggling alone with solutions on those. Okay, 1.37. Let's say we have a force equation. You might not know what force is, but hopefully I can remind you. Okay, here. Newton is a unit, and 1 Newton is a kilogram meter per second squared. I like to think of it as an mg. If you know these terms, great. If you don't, I'll remind you in chapter 5. B is going to be speed, and then C and D are unknown constants. Okay, our goal is going to be try to figure out the units of these constants. Okay, before we get into this, does this look like just some nonsense crap that I'm just making up to torture you? It probably, I would think it does, but it turns out this is an actual physics equation for drag. This is low speed drag and this is high speed drag. So this equation will, is there any aerospace majors in here? Moving on. Okay, never mind. But so if there was aerospace, they would find that interesting. Sorry about that. Okay, now here's a cool trick. You want to know this. You're tired, you want to go to sleep. Don't fall asleep on me yet. Check this out. The unit math allows us to make this simpler. What if you wanted to figure out the units of C? How would you approach that? Most of you would probably solve the equation for C, right? Wrong. Bad idea. What we could do is I could stick the units on here. The units of f are equal to the units of this plus the units of this. Well, let me ask you something. Apples plus apples equals apples, right? Or oranges plus oranges equals oranges. If we are looking at these strictly as units equations, I can actually pull this apart. The units of this have to equal the units of that. Separately, the units of this is equal to the units of that. So once you put those square brackets on and say we're in unit land, you can save yourself some time. In particular, this gives us two separate equations, which are very useful. The units of F equal the units of C times the units of V. Similarly, the units of F am I on the right whiteboard? Always like, you still out there? Can you see me, Alan?
Yeah, the board. Yep.
Yeah. So my screensaver kicked on. When the screensaver kicked on, did your screen go black or no?
No, we were still able to see.
Just making sure, just checking. All right, that saves me a lot of headache. Okay, thanks. Okay, so this is what's powerful. The unit math, we don't have to be correct algebraically, right? So then we can separate this out. Do you see how that makes it easier to find the units of C or D separately? So just remember that cool trick. All right. So in particular, let's figure this out. The units of C should equal the units of F over the units of V, right? Just rearranging this. Well, the units of the constant C, what were the units appropriate for the symbol F?
Kilograms or times meters.
Kilogram times a meter per second squared. And we're going to divide this by the units appropriate for V, which are
Meters per second.
meters per second. Now remember, the only difference between what I'm telling you and what Dom is telling you is he is saying just leave the brackets on the whole way, if I understood it correctly, right? You would leave the brackets on at that step, which is totally fine too. Yeah, it's right. It's a great way to do it. It's probably the right way to do it. Whatever. In this case, what's that?
I just made it up.
Oh, yeah, yeah. You got to have some way of doing it, right? So now, I know you guys are smart. I know you're in a hurry. I know you can do a lot of things in your head. I want you to pass your classes and I want you to get it done right. Take the time to just do this stupid step of multiplying by the reciprocal on your paper so that you don't screw it up when you're doing it in your head. I have made so many mistakes from trying to do steps in my head, and I've been doing this 20 years. Just let the paper do the work, right? And if you're saying, well, I don't want to waste paper, I'll tell you what's wasting paper. Taking my class twice, right? If you do the work on paper, you take the class once. Did I get it all? I was in a hurry. I was like in a fury of people not doing. What do we get out of all
I
this?
think you're missing one. Oh, wait, you're good. No,
Are we good?
yeah.
Weird unit, huh? Cool though. So if you're curious about this, I actually have an extra problem for aerospace majors, but since you're not, I'm not going to tell you about it, except I am because I can't help it. It's on page 15 and you can see aerospace, they actually take this another level. So if you're into that, or if you're a physics major, are there any physics majors? Let's hope not, for your sake. I love physics, don't get me wrong, but man, engineering is going to pay better probably. Probably have a better life. But so yeah, if you're into that, you can read about these things in parameter space, or if you're really passionate about that, ask me about page 15. I think we should stop there, right? Where are we? Oh my gosh, we're pretty good. I'm going to do something really quick. You guys can start packing up your stuff if you want, and then I'm going to show you something on the board before we get out. Oh, it's time to go, isn't it? It's basically right at time. Sorry, I'm late. But yeah, we've basically covered all of chapter 1. You know the problems to do the problems, get it done. we're gonna pick up on chapter 3 in the workbook, vectors, next time. Yes, questions?
Is it a good recommendation to finish the required problems like as the week goes by?
Ideally, you'd be doing the problems all the time and be finishing up like the day after I finish a lecture. In reality, like my A students from history have said, it's really hard to get them done right away, but they set a goal of no later than a week after I finish it in class.
Yeah.
Got it? So if you can finish chapter 1 and 3 this weekend and like, yeah, like if your other classes haven't ramped up yet, then you can get a little bit of an edge, that's gonna help. The key is you want to factor in time to take practice tests later, right?
Do you think that thing that I was taking help for as well in this class?
No, you can take whatever you want anytime, right? I used to take all kinds of weird classes, yeah.
It's not too much together, right?
No, I mean, you gotta work, right? So the key is you want to ask yourself, what else do you have in your life? Do you have a job?
No, just these classes, that's it.
Well, then you can do it, right? If you have a job or if you have family responsibilities or if you have to care for someone, right? That starts to add up.
Yeah.
Once you get over about 60 hours a week of real life, you're in trouble, right? It's because it's hard to keep up with.
I get that.
Yep. Yeah, I got a leaky fish tank. What's up? Oh, I'm gonna stop the live stream.